Lecture 2a, Plotting Motion with Motion Diagrams and Graphs. This lecture relates to Chapter 2 of your textbook, which is about the kinematics in one dimension. Kinematics is Greek for motion. Kinematics in two dimensions with the motion along curves, circles, ellipses, parabolas, and other curvilinear motion. That will be covered in an upcoming lecture and future chapter. The topics for this lecture are: what is displacement? How do we interpret motion diagrams, and what are they? How do we plot motion on a graph? What is uniform motion? And what is the difference between speed and velocity? So what is displacement? It is the change in the position of an object as it moves from initial position to a final position. X marks the spot, so X subscript I is our initial position. X subscript F, therefore, is the final position. Displacement is the change in position, so we read that equation as delta X. Delta is the Greek, that triangle is delta, a Greek letter. And anytime you see a delta in physics, it's a good bet it stands for a change. So delta X means the change in X, or the change in position. The change in position relates or equals or equates to the final position minus the initial position. Why is it final minus initial as displacement and not initial minus final or something else? Let's see with the example below. Sam is moving along 12th Street, going from start to end, or the direction of the arrow, which is a displacement vector. We see Sam is going away from the intersection to the right. The start and end mark the start of our observation and the end of our observation. It doesn't mean that Sam has started his motion and then ended his motion. It just means that's the start and end of our observation. Sam could very well be moving before the start of our observation. Sam could very well be moving after the end of our observation. All we're saying is between the start and the end, we have observed a displacement. The initial position is 50 feet, looking at the x-axis below, and his displacement has gone from 50 feet to 150 feet. He's increased his position by 100 feet along the x-axis or to the right of the intersection. So going back to our equation, final minus initial would be 150 minus 50, or 100. Positive 100, the same as we easily see on the graph below. If it was initial minus final, which it is not, then that would be 50 minus 150, which would give us negative 150 feet. Negative 150 feet would tell us that the object, in this case Sam, is moving to the left of the x-axis, or decreasing or going towards the negative direction on the x-axis, going towards the intersection. But clearly that is not the case. He is going away from the intersection in the positive x direction. So our displacement is final minus initial. It gives us the correct sign, or the correct direction of the displacement. Starting 50 feet, increasing or displaced by 150 feet to the right, puts them at a final position of our observation at 150 feet. The 50 feet is measured from the intersection. That's where 0 is. The 150 feet is also measured from the same location, the center of the intersection, where 0 is. That's what we call our origin. If you're following along, you should be able to answer this question. A dog is at position x equals 33 meters. The dog then undergoes a displacement, a delta x, of negative 40 meters. Therefore, what is his final position? Is the dog at negative 7 meters, negative 40 meters? Or is the dog's final position 33 meters or positive 73 meters? Submit your answer on Blackboard. Under the Lecture 2a questions, it should be identical to this. Pause this lecture slide to do so, and then play it when you return. If you have successfully answered the question, you use the equation previously. Displacement is final minus initial position. But we're asked to solve for the final position, so we rearrange the equation. Displacement plus xi, or plus the initial position, to find the final. The initial position is 33, so 33 plus the delta x plus the displacement of negative 40. So negative 40 plus 33 is equal to final position, which gives us the right answer. Another example of displacement. This boat is moving along this river. Displacement vector, the arrow, from the boat's initial position to the boat's final position, marked on the picture, xi, and xf at the head of the arrow, tell us the boat has moved down the river or along the river. But notice the displacement vector from final to initial is not the same thing as the path of the boat. The displacement vector starts at the object's initial position and ends at the object's final position. the two images of the boat. It concerns the change in position, as we have just seen, final minus initial. The change in position is the length of that vector, the length of that arrow, final minus initial. The length of that arrow is the displacement. The displacement does not matter what the object did in between these two positions. The boat did not follow the displacement in the sense that it did not move along the arrow. The boat went along the river, which is a longer path than the length of the arrow. It's a longer path than the displacement. Displacement and path are not the same thing. The boat could have taken an entirely different path. If the initial position and final position are the same, the displacement would be the same. The boat could have stopped along this river and then started up again and still ended up at the final position, and it would have the same displacement. Displacement just contains information on the distance and the direction. The distance between final minus initial and the direction, going from initial to final, going from the tail to the head of the vector. Displacement is not dependent on an arbitrary origin. Let's see the last example to see what that means. We said the origin was at the intersection. That's where we marked 0 feet. To say Sam is at 50 feet, he's got to be 50 feet from something. To say he ends at 150 feet, he's got to be 150 feet from something. If we instead choose the origin to be the start of our observation, the initial position of Sam, then he would be at 0 feet. And then the end of our observation, his final position, would be at 100 feet. Because his displacement is still identical, going from 0 to 100, or 100 minus 0 to get the same displacement. If we chose the end position to be the origin, to say that's the 0, then where would Sam start? His initial position would be negative 100 feet. He would go from negative 100 feet all through the negative numbers up until 0, the end of the observation, which would be our arbitrary origin, negative 100 and 0. 0 minus negative 100 is positive 100. It is the same displacement in all three cases. The displacement is physical. The origin is just arbitrarily chosen. The positions, therefore, the value of the positions, 50 feet, 150 feet, or 0, 100, and negative 100, and any other numbers we can come up with for the measurement of positions, are arbitrary, relating to an arbitrary origin. But the differences between those positions, the displacement is not arbitrary. That is a physical. That is the motion of Sam, or the motion of the boat. Regardless of what values we use to pick those positions, the displacement between them represents the physical motion. Displacement versus path, as we saw, is not the same thing. Another example, say you're at the top of a ski slope and you're skiing down the ski slope. The path down a ski slope can vary, but the displacement from initial position at the top to the final position at the bottom can be identical. If you start at the top and you go down the ski slope on a long, windy path, curving back and forth, wedging your skis nice and slowly, and ending down at the bottom where we've marked the head of the arrow, your displacement can be identical to somebody who goes straight down, does not swerve back and forth at all, as fast as they want, but if they start at the top and end at the bottom, the same final position where the head of the arrow was marked, they would have exactly the same displacement, even though the path would be different. Somebody can start at the same top of the ski slope and go down a different ski slope, and if they end at that same point at the head of the vector or the arrow, they end at the same final position, they would still start at the top of the mountain, take a different route, and get to the same final position. Their displacement would be the same. Somebody who starts to go down halfway, stops for a snack, maybe hikes back up to get their skis, and then skis down and ends at the same final position would still have the same displacement, because it's just difference between final and initial, which is the same in these cases and many others. Another example of displacement versus path. What is the average displacement of players during a basketball game? Well, displacement depends on final and initial positions. So let's think about those states. What is a good initial position? Well, when the game begins, players are gathered around the midcourt or the half court. So the average position for players is the middle of the court. When the whistle blows, the end of the game is a good final position, and players are scattered all over the court. Sometimes some of the players will be under one basket, sometimes they'll be under the other basket. Some players will be on one side of the court, and the other side of the court, or all over the court when the final whistle blows. On average, the players can be anywhere. So on average, the final position is again the middle of the court. Just as often the players will be on one side or the other over successive games at the end of when the final whistle is blown. So the final position is the middle of the court, and the initial position is in the middle of the court. So what is displacement? It is nothing. Final minus initial, if they are the same, gives you 0. There is no displacement. But the basketball player may very well disagree, because he's been quite tired after running back and forth along the court for the entire duration of the game. His path is far different from nothing. That's why he's exhausted. He's covered quite a distance. But distance or the path is not the same thing as displacement. Motion diagrams. The film strip to the left is an example of a motion diagram. We can easily see that the car is moving to the right at a constant speed from this film strip. How do we know this? The duration of time between each frame is the same, and we see the displacement of the car between each frame is the same. So it has the same displacement in the same successive times. Hence the car is moving at a constant speed to the right. The illustration on the right is the same idea. It's the same car. The 4 images of that car is at a later time. So the same amount of time has elapsed between each image of the car, and we see it's the same displacement between each image of the car. The same displacement and the same time means the car is moving at a constant speed. Without the need of drawing a film strip, on one drawing, with 4 images of the car over 4 successive times, we get the same information of a car moving at a constant speed to the right. When an object moves at a constant speed, we say its motion is uniform. And hereafter we'll call this uniform motion. In this illustration from your textbook, we see the car is slowing down. The displacement between the car's images is less over the same time frames. So less displacement over time means the car is slowing down, as clearly can be seen. In part B of this image, the car has been represented by a dot. 0, 1, 2, 3, and 4 represent the images of the car over subsequent times. The same amount of time has elapsed between each dot, just as the same amount of time has elapsed between each image. The time could be 0 to 1 second, 1 to 2 seconds, 0 to 1 minute, 1 to 2 minutes. It could be the same fraction of a second between the dots. The dots we call the particles, representing the object, the car in this case, as a particle. It could also have been Sam, or any other object that's in motion. We don't treat the object's shape as important for this first unit and just represent it instead by a dot or a particle. So a particle that's moving the same way as the car would have the same motion diagram, which represents that it is moving in the same way. So in this particle motion diagram, these dots show us that the displacement is decreasing over time going from 0, 1, 2, 3 to 4. Every position of that dot, from 1 to 2 to 2 to 3 to 3 to 4, represents the same amount of time that has elapsed. So from 0 to 1, it's a greater displacement for the same amount of time between 1 and 2, and less displacement for the same amount of time between 3 and 4. So displacement decreasing over time means slowing down, of course. Another example of a motion diagram is popular in sports. These images from the Winter Olympics show that the figure skater and the skier are in motion and changing the motion. First, the strow motion of the skier going down the slope. We see the displacement is decreasing for the first portion of the skier's motion down the slope, and they're changing direction. So the skier is slowing down as they're making the turn. Where the images of the skier get cluttered together, displacement is less for the same elapsed time between each image. Then the skier has made their turn, the displacement is increased. The skier is increasing their speed as they're going down the slope, and then slowing down where the images get cluttered together, and then increasing the displacement again. So the skier is slowing down, speeding up, slowing down, and turning. All that can be seen easily in this motion diagram. The same thing can be shown with the figure skater. As she jumps up, her images are getting cluttered together, so she is slowing as she is moving to the right when she jumps. And then when she has returned to the ice, her displacement is increasing, she's picking up speed. What can't be shown with a motion diagram, a particle motion diagram for the figure skater, is that she's spinning or rotating about herself. We can easily replace the figure skater and the skier with dots or particles and convey the same information. Except for the figure skater, as she's spinning about herself, our particle motion diagram, our dot, can't represent that. We will deal with spinning or rotational motion later in the semester. In this image from your textbook, the motion diagram represents Alice, who's sliding along a smooth icy road on her sled when she suddenly runs headfirst into a large, very soft snowbank that gradually brings her to a halt. We see the motion diagram is giving us the same information. The first portion of the motion diagram, this motion is at a constant speed because the displacement vectors between the particles are at a constant length. In motion diagrams, the displacement vectors span successive particle positions. The particle positions, or the displacement vectors, are shrinking after Alice hits the snowbank, representing that she's slowing down. Less displacement over time, slowing down. Or she at first is in uniform motion when she's going over the smooth, frictionless ice, and then she's in non-uniform motion when she's slowing down from the friction from the snowbank. In this illustration from your textbook is a race between the hare and the tortoise. The hare's displacement vectors are greater. The motion diagram is showing greater displacement over time. The hare is moving faster than the tortoise, but notice both the hare and the tortoise are in uniform motion, just different uniform motions. A constant speed for the hare and a slower but constant uniform motion for the tortoise. All that is easily represented in the motion diagram without having to draw a hare or a tortoise. Speed is distance per time. Looking at the motion diagram for a race between a car and a bicycle, we can calculate the speed from motion diagrams. We see 0 seconds, 1 second, 2 seconds for both the car and the bicycle. The displacement vectors, the length can be determined by the x-axis beneath the motion diagrams. Between 1 and 2 seconds, the displacement vector for the car goes from 40 feet to 80 feet, or 80 minus 40, final minus initial, gives us 40 feet. And the duration of time between 2 seconds and 1 second, or 40 feet in 1 second. So therefore its speed is 40 feet per second. You should be writing down this equation and doing the calculations for each one of these examples. The car also moves 120 feet, the full displacement in 3 seconds. So 120 feet divided by the duration of time, the time interval of 3 seconds, 120 divided by 3 is of course 40 feet per second once again. The car is in uniform motion at a constant speed, so it should be no surprise that the car's speed is 40 feet per second in both cases. Whether the duration of time is from 0 to 1 second, and therefore the final minus initial is 40 minus 0 over 1 minus 0 seconds, or it's between 3 and 2 seconds, 120 feet minus 80 feet final minus initial position divided by 3 minus 2 seconds would still give us 40 feet per second in all cases. The bicycle is clearly moving slower as its displacement vectors and the particles are bunched up in the motion diagram. The bike moves 40 feet in the first 2 seconds. So 40 minus 0 divided by 2 minus 0 is 20 feet per second. The bicycle is also in uniform motion, so every attempt I make to figure out the speed of the bicycle using different final initial positions will give me 20 feet per second. For example, the bike moves 20 feet in the first second, so therefore its speed is still 20 feet per second. And in the full duration of time, It went from 0 feet to 60 feet, or final minus initial, 60 feet minus 0, 3 minus 0, 60 divided by 3 is 20 feet per second. Velocity is not the same thing as speed. Velocity is displacement divided by time, whereas speed was distance divided by time. Herein lies the difference. Bike 1 and Bike 2 are both in uniform motion. If we look carefully, we can see that Bike 1 and Bike 2 have exactly the same speed. But what is the velocity of Bike 1 at 4 seconds? Well, at 4 seconds, the bike is at 80 feet. But we need to have a displacement, a change in position. So let's say from 0 to 4 seconds represents the displacement from 0 feet to 80 feet, or final minus initial. 80 minus 0 over 4 minus 0, 80 divided by 4 is 20 feet per second. If we went instead from 4 to 5 seconds, then final minus initial would be 100 feet minus 80, or 20 divided by 5 minus 4, 20 feet per second once again. And it's going in the positive x direction, it's going to the right. Its displacement is 20 feet per second, or positive 20 feet per second, or 20 feet per second to the right. What is the velocity of Bike 2 at 0 seconds? Well, Bike 2 is going from 120 feet to 100 feet. Final minus initial, 100 minus 120 is negative 20 divided by 1 minus 0, or negative 20 feet per second. So it's the same speed of 20 feet per second, but negative 20 feet per second tells us we're decreasing the value of x, going towards the 0, we're going to the left. So the velocity is the opposite, in a sense, of Bike 1 for Bike 2. Bike 1 and Bike 2 have the same speed of 20 feet per second, but their velocities are different. Bike 1 has a positive velocity of 20 feet per second, Bike 2 has a negative velocity, or the velocity to the left of 20 feet per second. Velocity is simply speed with direction. Can the velocity ever be in a different direction than the displacement? Well, the direction of the velocity comes from the displacement. The displacement, final minus initial, gives us the magnitude, the amount of the speed, and the direction of the displacement gives us the direction of the velocity. It's impossible to have a displacement going to the east, yet your velocity or your motion would be going to the west. That would simply be nonsensical. Your displacement represents the direction of your motion. Your velocity represents your displacement and direction of your motion in time, how quickly you're doing that displacement. So velocity and displacement always point in the same direction. The direction of the displacement dictates the direction of the velocity and vice versa. The reason I ask this question is not an uncommon mistake to have different directions, different signs for displacement and velocity. Be aware of that. Now let's take motion diagrams with some data and represent it on a plot. How do we take a motion diagram and graph this motion on a plot? First, let's look at the table of data from your textbook for measured positions of a student walking to school. We start our observation at a position we'll call 0. After 1 minute, the student has walked 60 meters. After 2 minutes, the student has walked 120 meters from the beginning time, or another 60 meters in the next minute. At 5 minutes, the student's position is 220 meters from their original starting position. At 9 minutes, the end of our observation, but not necessarily the end of the student's motion. At 9 minutes, the student is 540 meters away from their initial position of 0 meters at 0 minutes. From this data, we can make a motion diagram. Looking at the motion diagram, and then at the top right, the first particle, the first dot representing the student at 0 meters at 0 minutes. The next dot, the second dot, is the 1 minute dot, where the student is at 60 meters. The third dot is the 2 minute dot, where the student is at 120 meters. And the fourth dot lines up, the fifth dot lines up with the fourth minute of 200 meters at 4 minutes. We can see that the student is in uniform motion, moving at a constant speed from 0 to 4 minutes. We look at the data and we get the same information, but it's much easier to see on the motion diagram the displacement is the same over time for the first few minutes, and then the student is slowed down around and past the 200 meter mark. to a new, slower uniform speed. Uniform motion is constant at first, and then a slower uniform motion, and then a third faster uniform motion for the last few intervals, the last few displacements, the last few minutes. Now we can take that motion diagram and graph it. How we do this is we make a plot, a graph of position versus time. The dots represent the same particles in the motion diagram relating to the same data from the table. The first dot at 0, 0 is our origin. The second dot is the one that relates to the 60 meter position for the first minute. Second minute dot, 120 meters, and so on. So we've taken the motion diagram. The positions in the motion diagram line up along the vertical axis of the positions, and we take in sense the motion diagram, flipped it vertically to line up with that vertical axis, and then spread it out to the right over time. We then connect the dots, or interpolate, to assume that the motion between the dots is represented by the same motion that it has at the dots. From this we see that we have three slopes in part B of our illustration on the right. So we've taken this motion diagram and spread out the positions from the vertical axis, spread them out to the right over time, and now we have a graph with three slopes. These three slopes represent the three speeds, the three uniform motions of the student walking to school that we see on the motion diagram and that we can calculate from the graph. Slope on a graph is a rise over a run. The increase in the vertical is the rise. The run is the increase in the horizontal. Well, the increase in the vertical, the rise, is a change in position. The increase in the horizontal is a duration of a change in time. So a change in position over a change in time, we already know, represents speed. So the slope, the rise of the run, position over time, the change in position over the change in time, is the speed. So three slopes tells us there are three speeds. The steeper the slope, the greater the change in position over a change in time. The steepest slope is the third slope, which corresponds to the greatest speed, which we already have seen from the motion diagram up top. The shallowest slope, the one in the middle, shows that that's the slowest speed. It's the least change in position, the least rise for the duration of time. We could calculate the slopes to measure the speed the same way we can calculate the displacements to figure out the speed, in the same way we can calculate with a table of data the change in position over time. The graph is in many ways more powerful. It's quicker to create, and soon for you it will be quicker to interpret the motion on a graph. We won't be using motion diagrams much at all beyond this point, but you are responsible for understanding them. The understanding of a motion diagram helps you interpret the motion along graphs, which will be much more commonly used, and at first seems quite a bit more abstract. Let's practice with some graphs relating to motion diagrams. Again, from your textbook, these three motion diagrams we will graph their motions. So we see in the first part A, the first motion diagram, going from 1 to 6, that the position is changing, and it's changing with a greater displacement over successive times. The object is speeding up from 1 to 6. It could be an object that's speeding up on its way down. It could be going horizontally, or vertically, or going east or west, or north and south, or even ascending and increasing its speed. We're not told the direction from 1 to 6. All we know is the displacement is increasing over time. It's something that's gaining speed. It could be an object that's falling and gaining speed, or it could be an object that's gaining speed by some other fashion, a car starting from rest and accelerating to gain speed as it's going down a highway. We just don't know, but we do know it's increasing speed. B, the displacement is constant over time. It's uniform motion, whereas A was non-uniform motion. The object in B, uniform motion, could be descending at a constant speed. It could be drifting along ice at a constant speed. It could be an object, any type of object that's moving in uniform motion in some particular direction, the direction we're not told from these motion diagrams. In C, could be an object that's falling vertically but slowing down somehow, maybe by having a parachute opened. It could be an object that's slowing down by applying the brakes as it's moving along a road. It could be any object that's slowing down. From 1 to 6, the displacement is decreased. Now, in the next video, we'll see how we take these motion diagrams and plot them on a graph. Again, the trick is to take the motion diagrams, treat it as the vertical axis, the change in position, and then spread it out over time. Let's see that with the upcoming video. Before you look at the video, though, you should practice making each one of these motion diagrams into your graphs. By practicing these graphs before you see the video, you'll have a better grasp of the material. When you're done with the video and done